Hello, my name is Alejandro Ibarra Polanco, and I'm going to present the paper Delay Wreaks Havoc on Your Smartphone, Delay-Based Automation Interference Attacks. First, I will start with the paper overview. The acknowledgments goes to the authors Hao Tianqi and Chenglong Fu from Temple University, Qian Zheng from the University of South Carolina, and Xiaoyan Lu from the Stevens Institute of Technology. This paper was presented at the 43rd IEEE Symposium on Security and Privacy at San Francisco, California in 2022. The rapid development of the Internet of Things has led to different smart environments. One of these environments includes the smart home. This same proliferation of IoT devices has led to the devices to coexist using different platforms on the same environment. There's previous work that needs to be understood to understand the importance of this paper. The first topic to understand is that a lot of previous work talk about cross-rule interference, which refers to how many automatization rules in an environment can interfere with one another, for example, in a smart home. But one issue with these works is that they assume two things: all rules running on the same platform or different platform without interaction, and the second assumption is that all IoT messages are transmitted with identical delays. The second thing from the previous work that needs to be understood is the inference of information, such as home configuration, device information, applications, event or commands, automation rules, and routines, just by analyzing the encrypted traffic of a network. A highlight here is that by analyzing the encrypted traffic, so it doesn't even need to be decrypted to obtain all this information. The motivation from this paper is that real smart homes use more than one platform for IoT devices and automation, which is contrary to what previous papers explore. Also, this paper explores delay-based automation interference attacks, which are ignored by all the previous works. And the methods used by this paper is that it reveals 7 categories of delay-based automation interference attacks by using a smart home example. And after this, it uses 2 real-world testbeds, 2 real homes equipped with real IoT devices and applications to evaluate and validate all these types of attacks. The picture in the slide depicts a delay-based automation interference attacks. Platform A and B are running different rules. Platform A determines that a car is leaving, so the house enters in away mode and it closes the garage door. But the away mode is delayed to platform B. So when platform B closes the garage door, it will read as if there was a user, so it's not in away mode and it won't lock the front door, causing a security concern. This paper has 3 main contributions. It presents 7 categories of delay-based automation interference attacks, analyzes them, and demonstrates them. Also, it shows that these attacks do not trigger any alarms. The second point is that this attack takes advantage of the different path that messages in a real smart home with multiple devices and platforms have. And the third important point of the paper is that this paper shows that an attacker that wants to launch this type of attack will have the opportunity to launch this type of attack on a smartphone. Now, let's talk about the background and the attack model. Let's start with what a smart home is. A smart home is a home that has remote control and monitoring via IoT devices. A network of a smart home can be shown in the picture in the slide. Arrow number 1 shows devices that connect directly to the home router via Wi-Fi. Arrows 2 and 3 show non-IP protocol devices, for example, devices that connect via Bluetooth, that require a hub to convert the messages to IP payloads that are sent then to a home router. lines 4 and 5 shows that the routers can forward IP payloads to cloud servers and other devices in the LAN. Arrow number 6 shows that local platforms like a HomeKit can connect non-IP devices directly between themselves. Now, arrow 7, 8, and 9 show the different cloud-based IoT platforms, and they can be of three types. An endpoint, which mediates communication between devices and service platforms, which can be, for example, an AWS server. A service platform that obtains access to devices from endpoint platforms via cloud-to-cloud integration, for example, the if this then that. And the hybrid, which is the most popular and is a combination of an endpoint and a server, for example, Alexa and SmartThings. There are three different types of smart homes, and each presents their particular issues. The first one is single platform, single path, which is the type of smart homes that are studied in previous works. This is where all devices use the same communication path and use a single platform. This maintains the same order and consistency. For example, the picture on the top, that all devices are connected to an IoT platform through an IoT hub. Second one is the single platform multipath. This is where the devices use multiple paths but a single platform. This presents disorder but maintains consistency. Disorder is that the execution order of arrival is not executed in the same order. For example, there can be routine I that arrives first than J, but the actual execution can be the opposite. And then there's multi-platform, where there are multiple paths between devices and multiple platforms, which is shown in the last picture, where the WIMO plug is connected directly to a WIMO platform, is directly connected to a home area network via HomeKit, and is connected to the SmartThings platforms via a SmartThings hub. This causes disorder and inconsistency. Disorder, which was explained before, and inconsistency, which is that different platforms can have different readings on the same device. For example, a device can be on and off at the same time. This type of attacks needs selective event and command delaying. So IoT devices and clouds are constantly changing what's called heartbeat messages. This is that after several messages that are not acknowledged, there's a timeout and alarm is triggered, making the user know that the device is not responding. An attacker can become a relay mode in the middle of the devices to the platforms by using TCP hijacking, just in the picture below, where there is a client and a server connected, and the hacker uses a device to hijack that connection and put a man in the middle. After this, an attacker can recognize the events and commands from the packets and select which specific events or commands he wants to delay. And delaying messages is not going to be detected as long as this does not trigger a timeout. So as long as the heartbeat messages are not extended long enough to execute a timeout, it won't be detected. So who can launch this type of attacks? Any attacker that can eavesdrop and delay encrypted traffic can perform this type of attacks. This is done by compromising the Wi-Fi through RP spoofing or doing TCP hijacking. Doing this, the attackers obtain two capabilities: passive observation of the traffic and active delay of the events of commands. The picture on the left shows how an attacker is just eavesdropping the connection. This is to check the traffic, and it can detect the type of devices, the automation rules, the applications used, the platforms, and can deduct the user behaviors to know when to perform an attack or when to perform a delay. And the right picture, which is the same as the previous slide, shows a TCP hijacking, and this is necessary to be able to delay the attacks. Now let's talk about the delay-based automation interference attack themselves. The delay-based automation interference attacks, or DAI, are delaying selective events or commands to cause disorder and inconsistency. There are 7 types of DAI attacks that are going to be shown by using an example smart home. The example smart home is presented on this slide. I will explain all the 7 types of attacks using this smart home. The first attack is a condition overlapping attacks. Some automation rules won't run simultaneously if their conditions are exclusive. But if one of these conditions is delayed, these exclusive conditions will be executed concurrently. This exploits inconsistency, and this is shown in the picture below, when rule I has 2 parts and rule J has a condition in the middle, and all 3 conditions are exclusive. But if we delay event 1 on platform A, meaning we delay the condition on rule I, the first condition will be extended, which will overlap with the second condition on rule J, which will overlap with the second event in rule I. So there will be 2 time zones where exclusive conditions will be overlapping. And there's 3 sub-attack types on this. The action conflict, which is shown below, 2 different actions that are exclusive happening at the same time. An infinite loop, when, for example, there's a condition for light on and a condition for light off, and those are triggered, so there's an infinite loop of turning the light on and off. And a chain execution, where 2 conditions are chained, but they shouldn't be. Rule 2 is a trigger condition overlapping attack. This means that some automation rules avoid chaining the execution of 2 rules by making the trigger of one rule and the condition of another mutually exclusive, but a delay can break this exclusiveness. This exploits inconsistency. Let's say, for example, platform A running rule 6 and platform B running rule 11. Platform A runs when the user arrives, unlock the front door. And let's delay the user arrives signal to platform B. So platform B executes, the door is unlocked, but the user arrives signal is delayed. So it will say that the user is away when it is not. So it will sound the alarm and call the police even when the user is on the house, causing a false alarm. Rule 3 is a condition diverging attack, which is the opposite of the previous rule, but it causes inconsistency as well. This rule prevents rules with overlapping rules from interacting. 2 rules that should interact between themselves won't interact. Let's take, for example, rules 4 in platform A and 5 in platform B. Rule 4 mentions that when the car leaves, if in away mode, it closes the garage. Let's say that the away mode is delayed to rule 5. So the garage is going to be closed, but the away mode is delayed. So it won't lock the front door and the whole door, causing a security concern. Rule number 4 is an action disordering attack. This attack is changing the arrival of commands by different rules, and this can be caused by delaying the trigger event or the command. And this, in contrast to your previous rule, exploits disorder because it changes the execution order. We can see in parenthesis A in the picture that the trigger condition is changed. It's delayed. So the event triggers a condition, but this is delayed. So rule I that was triggered first is executed after rule J because the trigger event was delayed. Parenthesis B, the command is delayed, but the same output is obtained. So the trigger condition is on rule I and then on rule J, and that timing is preserved. But because the command was delayed, the command is going to be executed after rule J. Attack 5 is a condition disabling attack. This just says that if a rule's action changes a byte state to a value that dissatisfies the condition of another rule, causing a block. And this is a disorder attack. Let's say, for example, that an event is triggered and is sent to two different rules, but one rule is delayed. So let's say it goes to rule J and is delayed to rule I. When it goes to rule J, it is triggered, the condition is true, an action performs, but the event from that action causes the condition from rule I to be false. So by the time that the trigger arrives to rule I, that condition will be false, and the action won't be executed. Now let's talk about attack number 6, which is a condition enabling attack. This attack is called a condition bypass. That happens when rule J's action changes a device state to one that satisfies rule I's condition. So it executes rules that won't otherwise be executed at the same time, causing disorder. For example, we see rule 1 and 3. One says away mode and one says home mode. So if these are executed at the same time, it's impossible to have the two run together. But let's say rule 3 is delayed. So rule 1 executes, the door is closed, it goes to away mode, it is in away mode, so the garage door closes and sets a home mode. The delay causes rule 3 to execute after rule 1 finishes executing. So it will say the whole door is closed, and because rule 1 sets the home to home mode, rule 3 will open the garage, leaving a person inside and the garage open, causing a security concern. Lastly is rule 7, attack 7, which says that some rules are configured to run together, but the delay itself is a security hazard to this rule, and this just exploits the delay itself. Let's say, for example, that you can put the user in arrive mode from your smartphone in a remote location, and you want to do it like a couple of blocks before arriving home. So rule 6 is executed because it says the user arrives with you set up with your smartphone and you unlock the front door. But rule 7 is triggered saying that because you unlock the front door, there's an indoor camera to have security while you actually arrive to your home. If we delay rule 7, you will activate the user arrive mode, unlock the front door, and you won't have the camera securing the house, causing security concerns. There's two attack factors that affect the attacks themselves. First one is the loud message delay length. We talk about the heartbeat messages and how there's a time frame where the IoT device and the cloud are allowed to be disconnected, but it causes a timeout if it goes outside of that time frame. So that time frame is the allowable time that you can delay a message. And the second success factor is the user behavior. Knowing how the user behaves can allow the attacker to know when to execute an attack. Now, let's talk about the evaluation of the DAI attacks. The DAI attacks were evaluated into testbeds. These testbeds had the IRB approval, meaning the institutional review boards in the institution where experiments were conducted. All the two houses had real people living in them, and none of the people were the authors. House 1 had a couple, and House 2 had a single person. Each testbed had a router and Ethernet ports. These are the two testbeds and all the devices connected, also how it's connected to which platform. These are all the automation rules used on the testbeds. To simulate the attacker, a Raspberry Pi 4 Model B is placed in each testbed. IRP spoofing was used to turn the Raspberry Pi into a relay node that can delay, and examine the traffic. Then a script was used to examine the traffic and obtain the automation rules so that the attacker can know when to send an attack, a delay attack. All the attacks were performed based on the inferred home configuration obtained from the spoofing. To validate the attacks, the following methodology was used. The, the home users were instructed to perform several patterns on 2 different days to enable all the rules. Day one, they perform all the patterns to make sure all the rules were happening, and no delays were used. And this was the ground truth for day two, where the same patterns were made, but now the attacks were done by setting specific time periods to delay events or commands. And as mentioned before, the delay range is very important to the success of an attack. So the allowed delay length was obtained by the implementation and specification of the IoT devices or platforms. Also, the different traffic patterns were analyzed, the same traffic patterns that were obtained using the Raspberry Pi. All attacks were verified on this control environment when looking at the IoT logs. This means when looking at all the messages, the authors could see that all the attacks were successful. Now, when they look at the physical interaction of the sensor with the users, they notice that 2 attacks couldn't be verified, which is attacks 5 and 6 and 10 and 11. After being on a control environment, the authors wanted to investigate if an attacker in real life would get attack opportunities in a non-controlled environment. This is because on a non-controlled environment, an attacker needs to find the right time frame to perform an attack. And the methodology to determine if attack opportunities happen was the following. The 2 testbeds were run on a natural daily basis. So for a week, the home inhabitants just live their daily life without any instruction on which actions to perform. All the logs, all the events, all the commands, everything was analyzed after 1 week of the people living in there, and none attacks were happening. None attacks happened because they didn't want to put in danger the integrity of the inhabitants. But after all the information was compiled, to find out attack opportunities, there was a case-by-case analysis on the logs, executing every pair of rules. So for example, let's take as an example rules 6 and 7. The authors trace back the event logs to find the most recent away mode event, and they check if the away mode could be delayed enough without causing a timeout. An attack could be executed where the front and hold doors won't be locked. So they analyzed all the rules, took the user behavior, and analyzed if the time between the rules and the user behaviors allowed an attack to be performed. The result was that the average success for all the rules was 86.4%, and most attacks had 100% of success, while a few attacks failed. So in conclusion, the attackers will have sufficient opportunities to launch attacks, raising security concerns. And now, the authors also compare these methods to jamming methods. And why do they do this? Because contrary to the methods previously explained, where you need to hijack the connection, jamming does not require access to the Wi-Fi password. And they tried two types of jamming: micro jamming, where switching on and off disruptive signals in high frequency, but this didn't work because they only achieved a 10 millisecond delay, which is not enough to cause any harm. And random frames, that, as the name says, they just cram the medium with random frames. The issue with this method is that it dropped the events, meaning that the connection between cloud and device was lost, and, and the user will be able to detect the attacker. And while not all attacks were replicated by random frames, most of them were. Not all of them were able to be triggered because of the nature of the attacks. The paper also proposes an alternative method to the ones tested already. This new method is called reactive jamming. This method recognizes events and commands from encrypted traffic and can jam selective events and commands selected by the attacker. This jammer can block the N-1 retransmissions and let the end transmission pass, so this is a good method to avoid a timeout. The only downside from this method is that it requires a specific hardware. Finally, there's some countermeasures that can be taken into account. First, we can use better Wi-Fi password to avoid an attackers hack our Wi-Fi. Also, we can isolate sub-networks for IoT devices with more protection and causing more trouble for an attacker to hack the IoT networks. In addition, there can be enhanced security for IoT devices and hubs and routers. There actually exist devices that are resistant to RP spoofing, but this is vendor responsibility and is hard for the user to achieve. Another thing that the vendors can do is reduce the interval of the heartbeat messages to make it harder for the attackers to delay messages. Also, there are some synchronization and recovery techniques for handling inconsistency and disordering issues. Research is also happening and it's always advancing, and there's some state-of-the-art work that can be used to avoid this type of hacking. But this is very technical for the main user. The last security measure is enforcing security goals or properties, just enforcing certain rules to avoid the network to transfer to unsafe states. Let's go to the conclusions of the work. The authors made a responsible disclosure by reporting the event and command delay attacks to all the IoT vendors. Google, SimpliSafe, and Ring acknowledged the problem and mentioned they are already working or are planning on working on a countermeasure to the problem. SmartThings didn't make a reply, and Apple replied that this was an expected behavior and it was working as designed, although Apple allowed the biggest window for an attack. In conclusion, there was an introduced delay to IoT events and commands that didn't trigger alerts but caused harm to the users. These types of attacks are called delay-based automation interference attacks, and 7 categories were revealed, analyzed, and demonstrated into smart homes. Two issues were revealed on this paper: disorder and inconsistency. And some countermeasures were discussed, such as further research, better Wi-Fi password, APT spoofing countermeasures, and putting the IoT network in a subnet inside the Wi-Fi network. Thank you.